Everyone, thank you very much for coming. We're going to get started with the next session here. So this is called Beyond the Coprocessor, Lessons in FRC Vision and Localization. If you don't know me, so my name is Jonah. I am currently the lead software mentor for FRC Team 6328, also a student studying CS and math here at WPI. In terms of my background, so I've worked on a whole variety of vision systems for FRC, everything from retroreflective tape up through April tags and object detection. And I've worked both for 6328 and helping lots of other teams set up vision systems at all levels of complexity. So what are we going to focus on today? Well, as you may be familiar, 6328, we are part of what's called the Open Alliance, which means that we share a lot of the work that we do during the season. And that means that we also get a lot of questions asking for advice about vision. And we've learned quite a lot of lessons over the years about what works better and what doesn't. But what we've realized is many of those lessons have really just become institutional knowledge on the team, but never collected in any one place that we could point other people towards. So this session is really going to be my attempt to distill some of those most important lessons that we've learned about vision, both for us personally and in our experience helping other teams. Now, before we get started, I do want to set a couple of expectations about this. So first, I want to say you'll probably get the most from this presentation for those of you that already have a little bit of familiarity with the nuts and bolts side of FRC vision. The reality is that there are just a lot of basics that are a lot easier to learn by playing around with yourself. So I'm mostly going to be targeting this at the types of teams that maybe you've done vision for a year, you've tried it out, but you're not really sure where to go next. That's really, this session is going to be for you. The other thing I will say up front is that in general, this presentation is going to be fairly opinionated. If you've seen some of our sessions before, this is going to be more opinionated than most. And I expect there are people who will disagree with some of the advice I give. What I've tried to do, though, as much as possible, is focus on lessons that we have seen work consistently across a variety of teams and a variety of different games. You can talk to 100 teams and get 100 answers about what makes a good vision system, but there are lots of trends that we've found hold true universally, and that's what I'm going to focus on here. I'm also not going to talk a lot about specific hardware solutions, hence the title of the talk, Beyond the Coprocessor. I really want to focus on trying to give advice here that is helpful regardless of whether you personally prefer oranges, apples, limes, or raspberries, whichever fruit you prefer. So let's get into this. Now I said, first of all, we get a lot of questions about vision on 6328. Here are some examples of some of the questions that people ask us. And as I look to answer these questions, what tends to strike me is that many of these questions are missing the same important piece. All of these questions are asking about which options are better than others, but they tend to skip more fundamental questions. What is the purpose of vision? What are we trying to achieve? These are really important if we're going to evaluate which options make a better vision system. Unfortunately, it's really easy to get started designing a vision system from the bottom up with hardware and cameras and filtering algorithms. What we have tended to observe is that the best vision systems are almost always designed from the top down. Unfortunately, there are just a lot of teams that fall victim to the trap of black box localization solutions or chasing FPS with alternative vision pipelines, but none of that really matters if you haven't defined these goals ahead of time. So let's start by trying to answer these questions. Now, of course, when we're talking about the purpose of vision, this can change quite a lot depending on the season, team, and the robot. So let's look at a few examples from 6328 specifically. And we're going to break this down by game. This is not going to be a comprehensive list, but just to give you a taster. So in 2023, this was an interesting game. It was the first time April tags were included on the field. So no one really knew what they would be good for. By the end of the season, this is kind of a list of what we were doing with April tags, mostly thinking about auto alignment to the nodes and substations, but also figuring out how to reliably navigate the cable bump in auto. If you aren't familiar with this, basically the robot would go over this bump at full speed and tend to fly into the air, which makes odometry next to useless. So we wanted to address that issue. Now, 2024, this was the first shooting game with April tags. So obviously we were thinking about how to accurately score in the speaker. but we also wanted to know where the robot was when we were on the opposite side of the field in order to do accurate passing to our partners at the speaker. There were also more subtle features we wanted to implement with vision, where we would adjust the robot's behavior and the control logic based on our current role and our position on the field. There were a few things that used that. Now this year we didn't do a whole lot of auto alignment to score in the AMP. We'll talk about that later. There were some important lessons learned there. Now finally, 2025, most recently, this was our chance to revisit automatic scoring with a really precise task of placing the coral on the reef. And new this year, we also wanted to automate branch selection as much as possible, which meant the robot needed to know at all times which branches and levels were closest. This was also the first game that we personally started tracking game pieces on the field so that we could dynamically pick up coral from the ground in auto. That was a new thing for us. And again, we had a bunch of dynamic controls that changed based on where we were. Oops. Let me go back. Yeah. So there's a whole bunch of variation that you can see here between different games, a whole bunch of tasks. But what we started trying to do is seeing how can we group these tasks into buckets. Now first, all of the most important tasks tend to fall in this bucket of precise local positioning. This means that we are trying to determine the relative position of the robot in a particular field object. This is super useful for automatic alignment to scoring targets, both for pick and place and shooting style games. This also doesn't need to be particularly complex. I'll show some examples in a moment. And keep in mind that when we say precise local positioning, that can really mean all sorts of different things. For some games, you might need under an inch of precision to reliably score. But for example, in 2024, if we were within 6 inches of our target, that was plenty close. Now, precise local positioning doesn't cover everything. So the next category is imprecise global positioning. These are the types of tasks where we care about the robot's position relative to multiple objects on the field. For example, figuring out which field elements are closest. And for these, we don't need nearly as much precision. Even up to a few feet in many cases is plenty of precision to accomplish these goals. These tasks are also much more niche. So you will find lots of very highly competitive teams that don't pursue these goals at all. They're very much secondary. Finally, just for completeness, the last category of tasks is game piece localization. These tend to be the most different in terms of their requirements, though worth pointing out, not necessarily obvious when game piece localization is needed or not. For example, in 2024, we were dynamically selecting notes to pick up off the center line in auto, didn't use game piece tracking with vision at all. It's not always necessary where you think it might be. Regardless though, game piece localization isn't really going to be my focus of this presentation. There's a lot that we could say about that, but it's again sort of a secondary objective. Okay. So in summary, this is really the framework that I'm going to focus on, that we've seen define some of the best localization systems in the world. They are consistently achieving precise local positioning and imprecise global positioning. Now, I do also want to preemptively address a question you might have when I present this, which is, what about precise global positioning? Would that not be even better than imprecise global positioning? There are, though, a couple of issues with that. The most fundamental issue really is one of purpose. The reality is that global positioning is fundamentally more limited in utility than reliable local positioning, which accounts for all of the most critical game objectives. There are certainly items on these lists that benefit from global positioning. We have leveraged imprecise global positioning to great effect the last 3 years. The issue is that there just aren't a lot of game objectives where you benefit from knowing the robot's precise position when you're out in the middle of the field. We really only care about the robot's position to the degree that it affects our direct interaction with elements on the field. But suppose we envision some task that's not on this list that would benefit from that kind of very precise localization in the middle of the field. We would still have a really big problem. To explain, let's talk a little bit about coordinate systems. Now for local positioning, where we're positioning ourselves relative to a field element, all we care about are 2 transforms, which you can see there. The transform between the robot and the vision target, and between the vision target and our scoring location. Both of these are fairly well defined. The transform to the vision target is what we're retrieving directly from our vision system. We'll look at some algorithms for that in a minute. And the transform to the scoring location is fixed as part of a single physical object. So there is some variation, fields aren't perfect, but it's generally fairly well-defined and well-constrained. This allows us to precisely define the relative position of the robot and our scoring location. Now, at first glance, it seems like global positioning would be fairly similar. We can plot the location of the robot and a target like this. You can see a branch there. But how are we representing those positions? Well, we're using a global coordinate system, which is represented by those axes in the lower left corner. And we can represent any position on the screen using that coordinate system. Each pose here is represented with a transform from the origin to the pose. But what difference does that make? Why do we care what coordinate system we're using? Well, here's the difference. We have this really nice coordinate system with poses for each field element, but fundamentally, this is all a lie. The coordinate system here only works if you assume that every pose on every field element is in precise alignment with all of the other poses. But that will never be the case on a real field, regardless of what you might read about quarter-inch field tolerances in the manual. This means that really our nice, neat coordinate system looks more like this. It's very fuzzy and malleable. And our scoring target is more like a range like this. We know about where the branch is, but nothing more. So we can use these transforms to represent approximate locations. And even if you tried to measure the locations of every field element here, you'll find that they end up moving quite a lot as soon as robots start playing matches on this field. And to be clear, when I say that this is a limitation, I'm not talking about a technological shortcoming. Even the fanciest VR tracking system or a calibration utility doesn't change the fact that the coordinate system is fundamentally flawed. It's just a tool that we made up. It is a useful tool in general, but it's still a fixed coordinate system, and it still can't represent the nuances of an FRC field. I also don't want to give the wrong impression here that global positioning is useless. Imprecise global positioning is absolutely a game changer in FRC. We don't need a precise coordinate system to pick the closest target, to change our behavior based on field zones, or do some of the other behaviors we talked about. And depending on the use case, you'll find game piece localization can also fill in some of the gaps here. Global positioning is still absolutely a worthwhile goal of many vision systems, as long as we're clear about what it can do and what it can't do, and we're prepared to use other solutions to fill in its more fundamental gaps. Okay, so all of that was really just about setting the stage to define our goals. So now let's talk a little bit about how we can achieve those. And here, again, I'm talking about information that applies regardless of specific hardware. And we'll start by talking about local positioning. This tends to be the most important use case for vision, and for us, this is always the primary driver of many of our decisions. Okay, so in building a vision system, what better place to start than cameras? This is one of the trickier aspects of vision because it is so dependent on the game and the robot. But here are a few bits of advice that apply in most cases, and I'll show an example on a 6328 robot in a moment. So first, the do's. Definitely point cameras towards relevant vision targets. This may seem obvious, but I've also seen a lot of teams who just focus on maximizing field of view, on getting a 360-degree angle, but really, you need to be thinking about what are you trying to see and from what positions. That should be the main driver. Another thing to do is to choose a well-defined mounting location. In general, lower on the robot means that the camera's position will better match what you have in CAD. And also, in terms of a well-defined position, putting a camera on a moving part of the robot is generally a poor idea, just a good rule of thumb. You should also be including multiple cameras for different situations. There are sometimes cases where you can combine functionality where the same camera does multiple things, but usually you're requiring some amount of sacrifice. There are a lot of cases where it's just easier to add more cameras. Also consider using a variety of camera types. Vary your FOV, use monochrome versus color cameras. Different situations require different camera properties, and so you shouldn't constrain yourself to always using the same camera. Now, in terms of things not to do, for local positioning, as I said before, focusing on maximizing field of view is generally a poor objective. You want to be looking at specific parts of the field. Don't, as I said, mount it to a moving location. Compensating for that is possible, but quite difficult. Don't design an overly rigid mount. This one is a little more unintuitive, but in general, hard, rigid camera mounts are much more vulnerable if you get hit, and a cracked camera mount does you very little good. So 6328, we print all of our camera mounts out of TPU, so they're all flexible, and the number of camera mounts that we have cracked since doing that is very, very small. And finally, don't make access for maintenance an afterthought. Even after you make your vision system, you'll be needing to debug it, calibrate cameras off the robot. There's a lot of reasons that you want to be able to have access to it after the fact. Okay, for an example of what that looks like, here's our 2025 robot Manta. And diagrams like this are super helpful for figuring out where your cameras should be. And definitely take advantage of Robot CAD. You can place the robot on a field and check what all of your fields of view are, where they line up with field elements. It's super helpful. Now this year, we mostly focused on visibility when we're aligning to the reef. And the tricky thing there is the April tag can be in very close proximity in front of the robot. So our visibility is provided by two cameras that are actually pointing inwards to have this nice overlapping field of view where we can see tags very close. But we still wanted to provide a larger field of view when further away, so the cameras are spread out enough that we can do that. Now in the back of the robot, we also had a camera. There were two variations of this robot. When we were picking up coral with a hopper, we were using that back camera for alignment to the tag on the human player station, so it was angled up quite a lot to support that. And with the ground intake, the latest iteration, we angled it down and switched it to a color camera for game piece localization. So we're switching it based on the exact needs of what we need the vision system to support. Okay. Oh, that's very loud. There we go. Okay, so once we have a camera, let's think about how we can actually use that data. And there are a few options here that vary in complexity. The simplest option is what we can just call servoing. This means turning until your target is right in the middle of your camera frame. This is the easiest way to implement vision alignment, and there aren't a lot of points of failure. For a lot of use cases, this is plenty. The downside, so typically this requires a high frame rate on your camera, or additional implementation complexity to compensate for a lower frame rate. Also, generally this means your camera has to be perfectly in line with your scoring mechanism, so that at a distance you're lined up properly. And another key point here is that this alignment algorithm, or when you're developing an alignment algorithm, you can't operate in multiple axes if you're just doing servoing. What that means is you can pivot left and right, but you aren't going to be able to control your translation or the way that you approach the target, which can be a big issue for games like 2025, where you might want to come in straight onto the branch, for example. This solution doesn't really support that. Okay, so servoing was very common in FRC in the retroreflective era, so prior to 2023. But even then, many teams were frustrated by that limitation of not being able to operate in multiple axes. So trig-based solvers were an alternative that allowed us to calculate full poses. Remember, we're still talking about relative to the target, local positioning. And the way this works is you measure the distance to the target using the vertical angle of the target in the frame. You can sort of see a diagram there. The main limitation is that this requires a height difference between your camera and the target. So one is significantly above or below the other. This also relies on having a very accurate gyro position. That can be a major disadvantage at times, since even the best gyros can and do drift. If you want to see a demonstration of that, try running an FRC robot into a wall at full speed and see how your gyro likes that. The results will not be pretty. Okay, so trig solvers still have those couple of problems. One way to address that is to use full 3D solvers. These were possible to use with retroreflective tape. They're much more common with April tags. The idea is we use an algorithm to determine the 3D transform from our camera to the target. One of the most common is called solve-PNP, which is part of OpenCV. The advantage of this, one, it doesn't require gyro data at all. It works independently. We solve our robot rotation directly from the vision target. We also don't need any kind of height difference. That's really good for games like 2023 and 2025, where the April tags are basically on the same level as your robot. Now, there are some disadvantages here. In general, the results are going to be noisier than with trig-based solvers. And it also suffers from a problem called ambiguity. What that means is if you can only see a single tag in your frame, there are going to be two solutions, two possible poses that it will solve for. That doesn't happen at all with multiple tags, though, and there are ways to eliminate that problem, which we'll circle back to. Okay, so There are some limitations here, but both are solvable problems that require some additional thought to handle properly. Also to keep in mind here, some vision solutions may not actually provide enough data to do that additional filtering well. Limelight in particular doesn't really provide enough data to handle tag ambiguity properly, which is unfortunate, but hopefully will change in the future. But regardless, people started thinking about, as good as 3D solvers are, how can we address some of their limitations, like the additional noise? Now, for this section, we'll switch gears to a whole different class of algorithms that try to address that problem. Those are algorithms that combine gyro data with a 3D solver. There are a bunch of variations of this. You can see a ton of names up there of different implementations, but there are some commonalities around them. Essentially, we're using the stable gyro signal to increase the stability of our 3D estimates. Here in this example video, the red robot is a standard 3D solver, and the cyan robot there is our implementation of this combined gyro trig solver. So you can see it's much more stable. And this class of algorithms, it's becoming increasingly popular. It is still not the be-all, end-all by any stretch, though. In particular, it still requires a very accurate gyro, which can introduce significant errors if that's not handled properly. And the accuracy is sometimes very poor when in motion if you don't handle latency properly. This is particularly a challenge for Limelight that's trying to do this algorithm on a coprocessor versus on the Rio, so there's some additional latency. They're working on how to compensate for that. These solvers are also much more sensitive to poorly defined mounting positions, particularly when you're tracking tags at a long distance, which tends to make them better for local positioning rather than global positioning. Okay, that was a whole bunch of information talking about different solvers. Here's a helpful summary chart. You will still find teams that are using all 4 of these solvers, so all of them absolutely still have a place in FRC. And there's no one right answer for every situation. Each of these solvers has its own quirks and limitations that require thought to handle. For reference, our current vision system mostly relies on a combined gyro and 3D solver for local positioning and a pure 3D solver for global positioning. Speaking of which, talking about global positioning, we can switch gears now and talk a little bit about how we can extend this simple local positioning system into full global positioning. There are a couple of unique considerations that come into play when designing a system that also does global positioning. And specifically when I say that, remember cameras on the front for tracking the speaker, but that back camera is positioned specifically to increase the total field of view of the vision system across all of the cameras. We want to make sure that we're tracking April tags even imprecisely, regardless of the robot's orientation or position. That back camera is actually a wide-angle lens, so it's about 90 degrees. A good example of how you shouldn't be afraid to mix up camera lenses and types based on the requirements. Also an important warning here, we're talking about maximizing the total field of view of the vision system, but we should be careful when talking about individual cameras. It's typically a bad idea to go with cameras that are wider than about 100 degrees. The standard camera model, which is called the fisheye model, breaks down above about 100 degrees with really wide-angle lenses, so pose accuracy will tend to be really poor with those. In general, just running multiple cameras that are getting close to 100 degrees, 90, 100 degrees, tends to work much better than a single very wide-angle camera. We can also, in terms of maximizing field of view, get a little bit more precise. This year we actually built this tool to figure out how to maximize our camera visibility. Basically, we sketched out this path in Choreo that showed sort of an example of what the robot might do. And we could analyze from a robot relative perspective which tags were visible from which angles. So the heat map on the right shows the total visibility of tags looking in different directions from the robot. And what you see here is actually not uncommon, that for a lot of games and a lot of use cases, if you account for typical robot patterns, the distribution of tags around the robot tends to be relatively even. That's hence the recommendation for maximizing the total field of view. You want to maximize the time that you're seeing any tag, even imprecisely. Now, you can also, of course, analyze this for specific games, specific robot movements, in case there are ways to optimize further, bias your cameras towards one direction or the other. Okay, so in the last section, we spent a while talking about solvers. How does that kind of translate over? Well, some of these solvers are better for local versus global positioning. The first note is if we're doing global positioning, we definitely need full poses, so we can eliminate a few options off the bat. But that leaves these three options. Now, increasingly, trig solvers are becoming less and less common. You can kind of see why if you look at that diagram. If you incorporate data from a 3D solver and combine that with the gyro, that removes the need for a height difference, which is a massive win in games with low April tags. Including gyro data also produces more stable poses and makes mounting accuracy less sensitive. But as great as those solvers are, pure 3D solvers still have a really important role. As I said, 6328 uses them for global positioning, and that's because we don't want to rely on a perfectly accurate gyro and maintaining that throughout the match. In fact, we use data from this global 3D solver to correct our gyro estimate over time, which in turn improves the accuracy of our local estimates. So they really have very different roles in that pipeline. Now, of course, 3D solvers also require a little bit more work to get the appropriate tuning and filtering. An important consideration here for global positioning as well is whether each of these solvers can incorporate data when you have multiple tags in the same frame. And generally that improves accuracy and stability quite a lot. And there are variations of all of these algorithms that can support that, mostly for 3D and combined 3D gyro solvers. So something else important to pay attention to. I also want to give sort of a good rule of thumb regarding error for all of these algorithms. All of these algorithms have error. 3D solvers tend to suffer from greater noise, but with lower bias. What that means is that there is higher variation in the individual observations you get, but they tend to be centered on the correct position regardless of distance. The other two options suffer more from bias, but with lower noise. So there's less variation in the individual estimates, but particularly as you get further away from the target, you'll find that those estimates are consistently offset from your real position. Both of those are possible to deal with in appropriate moderation, though generally we find that noise is easier to compensate for than bias. Okay, now regardless of the solver you choose, as I said, they all have noise, which means that global positioning always requires good filtering. You can sometimes get away with that without local positioning because you're dealing with a very constrained environment, but global positioning involves multiple cameras, tags at a variety of distances, and multiple kinds of error. You may, from time to time, run into template code that uses vision for global positioning but doesn't properly account for filtering. Generally, as a rule of thumb, you should be suspicious of anyone saying that filtering is unnecessary or an afterthought. It's absolutely critical for global positioning, regardless of the algorithm you choose. Now, there are a lot of techniques you'll see here. Here's sort of a quick summary of the most common that we see in terms of good filtering algorithms. First, for 3D solvers, you need to resolve any of those ambiguous estimates I talked about. You can check the relative reprojection error, so the quality of those two measurements. Some estimates are just really ambiguous and they're not really usable, but some are close enough that you can disambiguate them through other means, either by looking at reprojection error or comparing to another source of truth like your gyro estimate. In our case, we use that gyro estimate to disambiguate tags, and we have some additional logic, so we will only update our rotation estimate using vision if it was based on unambiguous estimates. So all of these things are really playing into each other. Now, the next step, some estimates are just really poor, and they need to be thrown out. That includes, we check, for example, that the z coordinate of our estimates is somewhat realistic. We check that we're within the field boundaries, because bad data can really mess up all of your other estimates. We then, for each individual estimate we capture, we want to calculate some kind of trust metric for how good that measurement is. Typically, that's in the form of a standard deviation if you're using the most common pose estimators, but generally we find it's not actually very useful to think about it as a standard deviation with units. You could try to measure it in theory, but really it's just a generic tuning metric, and you'll get the best results through trial and error, looking at the results and going from there. Each of the estimates that we're capturing from our cameras, we need to calculate that metric separately though. So we include metrics like the distance to the tags, or in our case specifically the square of the distance, looking at the number of tags, properties of the camera. For example, zoomed cameras tend to be less noisy because the tags are bigger in frame. And finally, we have all of these estimates with trust metrics. We can fuse them all together. Generally, WPI-Lib's pose estimators do a great job of that. You can also customize them a little bit if you need to fit different architectures or address some of their quirks. Those of you who have played with them might notice that, for example, if your gyro offsets conflict with each other, you might sometimes get fun orbiting motions. There are reasons for that, but sometimes it may not be desirable. So lots of ways to do pose estimation, fuse estimates. And at the end, you get nice clean poses that you can use in alignment algorithms or other parts of your code. Okay, now obviously there's a lot of steps there. There's a lot of complexity with creating that kind of filtering algorithm. One of the key tools in our tool belt has been log replay with AdvantageKit. Basically, this is our logging framework that allows us to develop filtering pipelines based on real log data with real field conditions, in addition to a whole bunch of other areas unrelated to vision. I'm not going to go really in depth on how this works. We've presented whole conferences about this before. The documentation is linked there. You can find more information and recordings of those conferences if you're curious. Okay, now finally, here's just a fun example to show sort of the importance of why we do all of that filtering and focus on having a wide field of view with multiple cameras. This is from our first 2024 event. So in the center there with the real solid robot, that's with all 4 of our cameras, all of our normal filters running. The yellow robot here shows if we only had 1 camera, but with all of our standard filters. So you can see that becomes offset when we're in a part of the field that we don't see a lot of tags. And finally, the red robot, which is by far the noisiest, we have all of our cameras, all of our full field of view, but we're only using very simple filters. We turned off most of this logic that we've developed. And you can see the estimates tend to be really poor doing that. So really all of these things have to come together to create a nice global positioning estimate. Okay, so we spent a while talking about how to make good local positioning systems and how to make a great global positioning system. But ultimately, we are creating one unified vision system. So how do we balance those 2 objectives? Well, first of all, you might be wondering, how do we separate the data for these 2 objectives in code? Do we need 2 pose estimators? Well, first, maybe not. We have used April tags for doing this type of localization since 2023, so for the past 3 years. And it was only this most recent year that we started explicitly separating local pose estimates from global pose estimates in our code. In a lot of cases, you can actually implicitly switch between these estimates using a single pose estimator. Here's sort of an example of what I mean. So here, this shows an example frame from our 2024 robot when we're shooting into the speaker. And up at the top, you can see the calculated standard deviations. So lower numbers means we're trusting that camera more. And most of the time, when we're moving around the field, there's no reason to trust any camera more than any other. Remember, April tags tend to be very evenly distributed around the robot. But here, when we're looking at the speaker and trying to shoot, we want to be using local positioning relative to that field object. And here, what you can see is the filtering object is trusting those speaker tags more. And in fact, that's not because it has identified those specific tags as ones to be trusted, but just because our cameras are positioned in such a way that those tags are clear and large in the frame. So it would want to trust them anyway, just implicitly. Here's sort of another example from that year. Here we're scoring in the AMP, and we want to rely on the tags that are closest to us because they'll have the least variation compared to the AMP position. So we strategically placed one of our 2 side cameras to have this great visibility to 4 tags on the left side of the robot. And the pose estimator is deciding to trust those tags more because they are large and numerous. Essentially what this means is we have a single pose estimate that's shape-shifting between multiple use cases. In the middle of the field, it's a great global pose estimate. And as we approach a field element, the tags that are nearby that we want to use for local positioning are implicitly trusted and used more, so we can rely on that same pose. I also want to note that all of those cases, when we're shifting between different pose estimates, we're always using the same coordinate system. We're always using this field coordinate system. The difference is that it's changing so that our robot pose is correct relative to different theoretical field elements. So we can measure relative to the theoretical location of the AMP and know that we're correct relative to the AMP in reality. Now, this is something we did really successfully in 2023. This worked great, given the positioning of cameras and April tags. 2024, the example here was actually a little bit of a lesson learned for us. In the specific case of aligning to the amp, even here, as we're focusing on those speaker tags, we were relying on distant tags in order to try and align. So what we really focused on in 2025 is making sure that we could focus on only the specific tags that we wanted in order to avoid any other interference. And the way we did that is to explicitly separate these global and local pose estimates. So we have separate pipelines, and we can tune them differently. So we're using different solvers, we're controlling for different properties, reducing latency versus maintaining smoothness. And in fact, in terms of local estimates, we were maintaining a separate local pose estimate for every individual April tag on the field. What that means is when our auto-align algorithm went to score on the reef, it was picking not just using the closest April tag, but whichever April tag it knew was correct relative to the branch that it wanted to score on. So it was very intentional, and there was no chance of interference from other tags on the field because that data was never incorporated into that estimate for each individual tag. Okay, so that's sort of all high level talking about how do we do local, global positioning, how do we bring them together. And here, finally, I want to finish by just sharing a collection of tips we learned along the way. These apply to all of the vision purposes I've talked about. There's a lot less to say about these individually, so we're going to do them a little bit more rapid fire, hence quick tips. Okay, first of all, there are a whole bunch of camera parameters that you'll probably encounter when tuning an April tag detector. And here's a quick breakdown of how those parameters will affect the quality of your results. I'll also link to the slides at the end, so if you want to refer back to this, you can. Now, notably, there are a bunch of trade-offs here where changing resolution, downscaling, brightness all affect your frame rate, which again affects the quality of your estimates. Generally speaking, the advice that I'd give is in terms of balancing resolution and frame rate, it's good to bias a little bit more towards increasing resolution. That tends to help you more than increasing frame rate, though some amount of balance between those is helpful. In general, downscaling, though it improves frame rate, is generally a poor idea because it affects the quality of your pose estimates and your range. Generally, downscaling is really only a good idea if you're on very low-powered hardware where you don't have another option to reach reasonable frame rates. And then brightness is another really important thing to tune, both with exposure and gain. The general advice is to keep this as low as possible that you can get away with while still seeing tags at the range that you want, because increasing brightness negatively affects your performance in general. Okay, another quick tip. So most cameras that you find out in the world are what are called rolling shutter. This means that they scan the image from top to bottom. And what that means is when you're in motion, you get really bad motion blur and distortion. Now for April tag tracking, what we really want is what's called a global shutter camera. That means the entire image is captured at once rather than scanning down. And here's an example. So we have a robot spinning at full speed on the left there. And from right in the middle of that video, we can capture the clean, undistorted image you see on the right. And we can track all of those April tags just as well as if we were stationary. This is also a really good demonstration of why you want to minimize the exposure on your cameras, because increasing exposure increases motion blur and makes stuff like this impossible. Okay, then another tip. So this one is particularly of concern to anyone using USB 2 cameras specifically. So to run at reasonable frame rates and resolutions in the bandwidth allocated to USB 2, these cameras tend to rely on image compression, specifically MJPEG compression. That can be okay for simpler pipelines, but the compression artifacts around April tags actually create additional noise that can affect your pose estimates. And it's not insignificant either. We've observed typical MJPEG compression can increase the noise in your pose estimates by up to about 40% or more. So the solution here really is either use a MIPI-based camera connected directly to a Raspberry Pi. So if you're using a Limelight, that's what's happening. Or for USB cameras, try and find a USB 3 camera specifically. They significantly reduce noise. They help with this problem quite a lot. Okay, next bit of advice, always make sure to calibrate your cameras. Regardless of the complexity of pipeline you're running, calibrating your cameras with a board like this is a Taruko board, will significantly improve the accuracy of your pose estimates. You can find more information about how to do this well in whatever documentation for your chosen vision solution. They all support this. Also important to keep in mind, most cameras are built to relatively poor tolerances. They are very much consumer grade. So expect that you will need to individually calibrate every camera on your robot, even if they are nominally the same model and lens. They are all going to be slightly different. The reason for that is that most cameras are really just not built for machine vision, so most of them don't support that. Sort of an interesting anecdote is there was a time in 2023 where we had 4 cameras on our robot, all identical. We mixed up the calibrations at one point. We were able to figure out which one corresponded to which camera by simply testing them out and seeing which ones were good and which ones were bad in terms of the quality of the pose estimates. It was really dramatic in terms of what difference it made swapping out those calibrations. Okay, next tip. So this one mostly speaks for itself. Most of your cameras will need to be individually calibrated or focused to an appropriate distance. Here's an example of a match where a camera lens was not properly secured and we drift out of focus. So even though this April tag is quite close, we can't see it at all. So that's a big problem. It's really important to focus your cameras ahead of time and secure them in place however the manufacturer recommends. Generally, it's also good when you're focusing cameras to bias towards a slightly farther distance if you're trying to do global positioning, because even a tag that is closer, if it's slightly blurry, it's large enough in frame that generally you won't have trouble detecting it, but it's more of a concern at greater distances where you'll lose that detection if you're focused too close. Okay, then another important one, when we're talking about vision systems, between capturing an image itself and that detection result arriving at the RoboRio, there's going to be significant latency. Depending on your frame rate, that could be up to a few hundred milliseconds. Here's a clip where you can see the robot moving quickly. Those pose estimates arriving at the Rio are shown in green, and when we're moving, they're lagging quite a bit behind the robot's real position. If you try to just integrate those poses naively, as you start moving, they will actually drag your pose estimate around and increase the error quite severely. And so you should check the documentation again for your chosen vision solution, how to properly account for that latency. WPI Labs Pose Estimator is set up to support this already, so you just need to make sure to plug the right things together. Another fun story about this, so at our first event in 2024, we were having major issues where our robot was running away from the center line, towards the center line in auto, and our pose estimates were all becoming offset. What we realized after the event is that the reason for that is we were accounting for latency, but our measurements were off by just 1 frame, 20 milliseconds, which massively affected our accuracy when moving at high speed. So getting this right is really important. Okay, so now circling back to sort of the topic of questions that we get from teams really commonly, one of the big ones is how do we utilize that field calibration time that we're allocated at events? The main thing really to remember here is that a great vision system is already designed to be tolerant to a wide variety of field conditions. In general, that makes field calibration less important, but there are still a couple of important things to check. And there are really 2 things that we always do during field calibration. The first is check for major field errors. Examples would include April tags that are simply in the wrong location, swapped with each other on the field, which we have caught before at our events. The robot was very confused when it saw those. Here we're more concerned about outright errors, not fields that are slightly out of tolerance. In general, trying to measure every field element or April tag location is rarely very useful, and really it's more a sign of a vision system that is not designed to properly cope with the natural variation in fields. The other thing that we do always is check our camera brightness. Fields have different lighting, it'll vary from your shop. Practice fields and competition fields might also have different lighting even at competitions. So you want to be adjusting your exposure and gain by putting the robot in common locations and checking that you can see all of the tags that you know you need to see. Now here we actually, after our first event when we're setting up a new vision system, we actually don't tend to adjust our exposure that much. At least here in New England, lighting seems to be consistent enough that it's not a major issue, but it's always good to double check. We always do this during field cal. Okay, and finally, just to finish us off, this one isn't very common yet, but I've included it in the hope that it will become more common in the coming years. It's a really helpful idea to record video from your onboard cameras if you can to help with debugging. Some teams do this just by doing a screen recording of their dashboard. That can be a really easy way to do this. Photon Vision also has options where you can capture snapshots during a match, which gets you part of the way there. And hopefully in future years, there'll be more support for doing onboard vision recording. This is something that we were testing out this year. Fundamentally, this really just allows you to solve a whole class of problems much more easily. If you have a failed April tag detection, you can just look at the video and see, was that because of a shadow or poorly calibrated exposure or a damaged April tag? You can see on the right there, this is a real footage from our robot at Champs where we found an April tag that had this gash in the side that we couldn't detect. So we were able to work that out within 5 minutes of getting back to the pit and get the FTA to fix that. So we avoided the massive headache of trying to track down gremlins in our vision system. Actually, the experience of setting up this kind of video recording for the first time, I draw a lot of parallels to when we started doing robot code logging for the first time, which I've talked about in other conferences. Essentially, we were left asking ourselves how we ever got by without this tool for debugging, because it made so many things so much easier. Okay. So we're just about out of time, and that was a lot of details. So I just want to quickly circle back to the big picture. These are really the two key goals: precise local positioning, imprecise global positioning, that we've found to be that common thread between the very best vision systems we see in FRC. And of course, teams execute on these in a bunch of different ways. Vision is one of the most exciting areas of FRC software right now. There are new innovations that are coming out every year. But hopefully what I've talked about can serve as kind of a guiding framework as you work through thinking about those new technologies and working through these problems on your own. So thank you very much. There's a link to the slides there as well for anyone who wants to refer to that. Yeah. Okay. And since we are at time, so we're not going to do questions as a whole group, but I will be around if you would like to chat. I am happy to talk about this more. So thank you all very much. Yeah, yeah, good. Yeah.
Perfect timing.
Yeah.
Awesome. Thank you, everybody. Lunch is ready just across the hall, so feel free to go out that door and get in line for lunch there, and we'll come back in here. Feel free to sit in any tables, join in some conversations with other mentors and all of that. So see you back here in a bit. Sessions will resume at 1:30.